Picture this: a region of space so dense that not even light can escape its grip, a cosmic vacuum with the power to shred stars like tissue paper. Black holes are not just the universe's most enigmatic puzzles, they're monsters lurking in the cosmic shadows, bending reality itself to their will. But what happens when we push the boundaries even further? Imagine a black hole so massive it could swallow our entire solar system without a second thought, an entity with the gravitational pull of millions, even billions of suns. These are the universe's most colossal black holes, and they defy everything we thought we knew about space, time, and the limits of existence. Today, we're venturing into the heart of darkness to uncover 30 mind-blowing facts about these cosmic titans. From black holes so vast they anchor entire galaxies to ones that spin at nearly the speed of light, each fact will leave you questioning the very fabric of reality. Did you know, for example, that some supermassive black holes are so large they could fit multiple solar systems side by side within their event horizons? Or that their gravitational waves ripple through space-time, sending tremors across the cosmos? These aren't just astronomical curiosities, they're the engines that shape galaxies, the architects of the universe itself. What makes these celestial giants even more fascinating is how little we truly understand about them. They're not just voids in space, they're dynamic, chaotic, and surprisingly violent. Some blast out jets of energy powerful enough to sterilize entire galaxies, while others may hold the key to unlocking the mysteries of dark matter and the origins of the cosmos. By the time we're done, you'll see black holes in a whole new light, not as cosmic destroyers, but as the universe's most awe-inspiring phenomena. So buckle up, because we're about to dive deep into the unknown, where the laws of physics break down and the impossible becomes reality. Deep in the constellation Canes Venatici, nearly 10.5 billion light-years away, lurks a cosmic leviathan so enormous it challenges our very understanding of black holes. This is TUN 618, the largest known black hole in the observable universe. Picture a gravitational beast so massive it contains the equivalent of 66 billion suns crushed into a single point of infinite density. To grasp its sheer scale, consider this: if you placed our entire solar system inside TUN 618's event horizon, the boundary beyond which nothing can escape, you'd still have room for thousands more solar systems side by side. Even light, the fastest thing in the universe, would take weeks to cross from one side of its shadowy realm to the other. Scientists first detected this monster not by seeing the black hole itself, since no light escapes it, but by spotting the blazing disk of superheated gas swirling around it. This glowing ring of doomed matter, called an accretion disk, shines brighter than entire galaxies, making TUN 618 visible across the cosmic void despite its staggering distance. What's truly humbling is that this black hole isn't just big, it's ancient. The light we see from it today began its journey when the universe was less than a quarter of its current age, meaning we're glimpsing a relic from a time when galaxies were still taking shape. Studying TUN 618 pushes the limits of modern astronomy. Its extreme distance and mind-bending properties force scientists to rethink how black holes grow. Conventional theories suggest supermassive black holes form over billions of years by merging with smaller ones or devouring gas and stars. But TUN 618's sheer size, existing so early in cosmic history, hints at unknown processes. Perhaps primordial black holes born in the chaos of the Big Bang, or runaway collisions between galaxies in the young universe. Every observation peels back another layer of mystery, revealing just how much we still have to learn about these cosmic titans. While TUN 618 stands as a staggering outlier, its smaller, but still unimaginably massive, cousins are far more common than you might think. Nestled at the heart of nearly every large galaxy, including our own Milky Way, lies a supermassive black hole, silently shaping the destiny of stars around it. These cosmic heavyweights, ranging from millions to billions of times the mass of our Sun, aren't just accidental occupants, they're the unseen architects of galactic evolution. Their presence was first suspected decades ago when astronomers noticed stars near the centers of galaxies whirling at impossible speeds, as if tugged by some invisible titanic force. Take Sagittarius, a star, the Milky Way's own supermassive black hole. 4 million times heavier than the Sun, it sits 27,000 light-years away, a quiet giant compared to more active counterparts in other galaxies. But don't let its calm demeanor fool you. When clouds of gas drift too close, Sagittarius, a star, awakens, tearing them apart in brilliant flares that reveal its true power. Its discovery, along with others like it, didn't just confirm a theory, it rewrote our understanding of how galaxies form. Scientists now believe these black holes are more than just inhabitants, they're foundational. Without them, galaxies as we know them might never have taken shape. Their gravity acts like a cosmic anchor, stabilizing vast swarms of stars and gas. Some even suspect the energy released by supermassive black holes during their growth, phases through colossal jets and radiation, helped ignite the formation of stars in the early universe. It's a delicate dance of creation and destruction where these behemoths can both nurture and obliterate, their influence spanning billions of years. The more we learn, the clearer it becomes. To understand galaxies, we must first unravel the secrets of the dark hearts beating within them. The event horizon isn't just a boundary, it's the ultimate cosmic checkpoint, a one-way ticket into oblivion. Imagine standing at the edge of a waterfall where the current grows so strong that even the fastest swimmer couldn't fight their way back upstream. That's the event horizon in action. The point where a black hole's gravity becomes so intense that not even light, traveling at 671 million miles per hour, can break free. Once something crosses this invisible threshold, there's no turning back, no signal sent, no cry for help, just an irreversible plunge into the unknown. What makes the event horizon so fascinating isn't just its destructive power, but how it warps our understanding of space and time. Picture space-time as a stretchy rubber sheet with a black hole creating a bottomless pit in its fabric. The closer you get to the edge of that pit, the steeper the slope becomes, until the very concept of forward and backward loses all meaning. Time itself slows to a crawl near the event horizon, as seen by distant observers. A clock falling toward it would appear to tick slower and slower, eventually freezing at the threshold from an outsider's perspective. Though for the doomed traveler, time would feel horrifyingly normal as they're stretched and shredded by tidal forces. In April 2019, humanity finally glimpsed this elusive boundary firsthand. The Event Horizon Telescope, a global network of radio observatories acting as a single Earth-sized dish, captured the first ever image of a black hole's shadow, a dark silhouette encircled by a fiery ring of superheated gas. The target was Messier 87's supermassive black hole, 55 million light-years away, with an event horizon wider than our entire solar system. That glowing ring, that's the accretion disk, its light bent into a perfect circle by the black hole's gravitational grip. The dark center, the shadow of the event horizon itself, a void where even the universe's brightest glow is swallowed without a trace. This groundbreaking image didn't just confirm Einstein's century-old predictions, it gave us a front-row seat to the most extreme environment in existence. Yet for all we've learned, the event horizon remains packed with mysteries. Some theories suggest quantum effects might allow information to escape, contradicting classical physics. Others propose that what we call the event horizon might not be the true point of no return, but merely the last place we can still see the doomed matter before it vanishes forever. One thing's certain, every discovery peels back another layer, revealing just how much we still don't know about these cosmic abysses. Not all black holes sit silently in the void. Some are cosmic whirlpools, spinning so fast they twist the fabric of reality around them. These are Kerr black holes, named after physicist Roy Kerr, who solved Einstein's equations to reveal their mind-bending properties. Unlike their stationary counterparts, these rotating behemoths don't just warp space. They drag it along with them like a spoon stirring a cup of honey, creating a vortex where the laws of physics as we know them begin to unravel. The numbers alone are staggering. Imagine a black hole with the mass of millions of suns, spinning at nearly the speed of light, so fast that its event horizon flattens into a cosmic frisbee, while the space around it stretches into a swirling funnel called an ergosphere. Step inside this region and you'd find it impossible to stand still, no matter how powerful your rockets. Space itself is pulled along with the black hole's rotation, forcing everything, even light, to move in the same direction. It's like being caught in a riptide where the water isn't just flowing but bending the very ground beneath you. This spin doesn't just distort space, it unlocks bizarre phenomena. Near a rapidly rotating Kerr black hole, time dilation reaches extremes. A single hour for someone hovering at the edge of the ergosphere could mean decades or even centuries passing elsewhere in the universe. The energy harnessed from this spin is unimaginable. Some quasars, the brightest objects in existence, are powered by supermassive Kerr black holes, converting rotational energy into jets of plasma that blast across millions of light years. These jets, moving at nearly light speed, can outshine entire galaxies, proving that a spinning black hole isn't just a vacuum, it's a cosmic engine. Yet the most tantalizing possibility lies in what these whirlpools might conceal. Some theories suggest that instead of a crushing singularity at their core, Kerr black holes could harbor a gateway, a ring singularity, where space-time bends so severely that it might open pathways to other universes or timelines. Of course, venturing near would still be fatal, as tidal forces would tear apart any matter long before it reached the center. But the mere idea challenges our understanding of reality, hinting that black holes aren't just dead ends. They could be portals to realms beyond our imagination. What's truly humbling is how these discoveries reshape our cosmic perspective. A spinning black hole isn't just a static pit in space, it's a dynamic, writhing entity, proof that even the darkest corners of the universe are alive with motion and possibility. Every observation peels back another layer, revealing a cosmos far stranger and more vibrant than we ever dreamed. If black holes are the universe's most efficient destroyers, quasars are their dazzling alter egos, cosmic beacons so blinding they outshine entire galaxies. These brilliant objects, short for quasi-stellar radio sources, are actually supermassive black holes in disguise, wearing crowns of searing light. At their core lies the same infinite darkness, but with a twist: they're feasting. When a black hole gorges on gas, dust, or even entire stars, the doomed material doesn't vanish quietly. Instead, it spirals into an accretion disk, heating up to millions of degrees and glowing with the fury of 1 trillion suns before crossing the event horizon. That's the secret behind a quasar's brilliance. It's not the black hole itself shining, but the superheated banquet swirling around it. The numbers defy belief. A single quasar can emit 1,000 times more energy than the Milky Way, all from a region no larger than our solar system. To put that into perspective, if you placed a typical quasar 3,000 light-years away, about the distance to Earth's nearest star-forming region, it would outshine our sun enough to cast shadows at midnight. Yet quasars aren't just cosmic vanity projects, they're time machines. Because light takes billions of years to reach us, the most distant quasars offer snapshots of the universe's fiery adolescence. The record holder, J0313-1827, blazed into existence just 690 million years after the Big Bang, its light revealing conditions in an era when galaxies were still taking shape. What makes quasars truly astonishing is how they sculpt the cosmos. Their intense radiation and high-speed particle jets, shooting out at near light speed, act like interstellar blowtorches, heating surrounding gas and suppressing star formation across vast regions. Some astronomers believe this feedback mechanism prevented early galaxies from growing too large too quickly, effectively regulating cosmic evolution. Others speculate that quasars may have played a role in reionization, the epoch when the first starlight tore apart the fog of hydrogen atoms filling the young universe, rendering space transparent. Even today, dormant quasars lurk at the centers of many galaxies, including our own, their past outbursts etched into the chemical fingerprints of surrounding stars. Yet for all their fury, quasars are fleeting. A quasar's brilliance lasts only as long as its black hole has fuel to devour, typically tens to hundreds of millions of years. Once the surrounding gas is exhausted, the glow fades, leaving behind a silent supermassive black hole like Sagittarius, a star. That's why nearly all quasars live in the distant universe. We're catching them in their brief, glorious prime. Their lingering light, captured by telescopes like Hubble and James Webb, serves as both a beacon and a challenge, inviting us to decode the violent adolescence of galaxies and the insatiable giants at their hearts. In April 2019, humanity turned its collective gaze toward a shadowy giant 55 million light-years away and saw the unseeable. The Event Horizon Telescope collaboration unveiled the first-ever image of a black hole, capturing the supermassive beast at the heart of galaxy Messier 87. This wasn't just a photograph, it was a triumph of ingenuity, requiring 8 radio telescopes across 4 continents to sync with atomic clock precision, effectively creating an Earth-sized virtual telescope. The target, dubbed M87 star, weighs in at 6.5 billion solar masses, its event horizon stretching wider than Pluto's orbit. What emerged from petabytes of data was an iconic fiery ring encircling darkness, a visual confirmation of Einstein's century-old predictions on an unimaginable scale. The image revealed far more than a cosmic portrait. That glowing ring, it's the black hole's accretion disk, a maelstrom of superheated gas swirling at near light speed, its light warped by gravitational lensing into a perfect circle. The darker central region isn't the black hole itself, it's the shadow cast by the event horizon, a void where space-time plunges beyond the point of return. The asymmetry in brightness across the ring became a smoking gun, proving the black hole's spin drags space-time around it like a whirlpool, hurling matter toward us on one side at relativistic speeds while the other side recedes. This single image transformed theoretical equations into visceral reality, showing how black holes don't just consume matter, they sculpt light itself. Behind this milestone lay staggering technological feats. Each telescope in the array gathered radio waves at wavelengths of 1.3 millimeters, unaffected by interstellar dust. Over 5 nights in April 2017, they recorded synchronized data so vast it couldn't be sent. Digitally, hard drives were physically flown to supercomputers for correlation. Processing required algorithms to fill gaps between telescope locations, a challenge likened to reconstructing a piano concerto from scattered notes. The result proved black holes aren't science fiction tropes but observable phenomena, their structures matching general relativity's predictions even under extreme gravity. Yet mysteries linger. The image resolution, while revolutionary, remains fuzzy, like viewing a donut on the moon from Earth. Future expansions of the telescope network, including space-based antennas, may sharpen our view to spot intricate details like photon rings, light trapped in orbits around the black hole. M87 star's image was just the beginning, a doorway to testing physics at its limits, from quantum gravity to spacetime's fundamental nature. For the first time in history, we didn't just calculate black holes, we saw one, proving that even the universe's darkest secrets can't hide forever. Einstein's theory of general relativity didn't just change how we think about gravity, it shattered our understanding of reality itself. Picture spacetime as a vast, flexible trampoline where stars and planets create gentle dimples with their weight. Now imagine dropping a bowling ball onto that trampoline, warping the fabric so steeply that anything rolling nearby gets sucked inexorably toward the center. That's a black hole's grip on the universe, a distortion so extreme it twists the very rules of time and space. Near a black hole's event horizon, gravity doesn't just pull, it stretches. Astronomers call this phenomenon spaghettification, a gruesomely vivid term for what happens when tidal forces overpower an object's structural integrity. Imagine falling feet first toward a black hole. The gravitational pull at your feet would be exponentially stronger than at your head, elongating you like taffy until you're torn apart atom by atom. But it's not just matter that gets warped. Time itself bends under this immense gravity. A clock ticking near a black hole would slow dramatically compared to one far away, a phenomenon called gravitational time dilation. To a distant observer, you'd appear to freeze at the event horizon, your signals redshifted into oblivion, while from your perspective, time would rush forward as you plummet into darkness. This isn't science fiction. We've measured these effects. In 2020, astronomers observed a star called S2 orbiting Sagittarius, a star, our galaxy's supermassive black hole. As it neared its closest approach, the star's light stretched to redder wavelengths, its motion slowing as predicted by relativity. The experiment confirmed Einstein's equations with stunning precision, proving spacetime isn't a static stage but a dynamic, malleable fabric. The implications ripple far beyond black holes. GPS satellites orbiting Earth must account for time dilation without corrections. Their clocks would tick faster than ground-based ones, throwing navigation off by miles. Black holes simply take this to extremes, revealing spacetime as an active participant in the cosmos, not just a backdrop. Every observation peels back another layer, showing us a universe far stranger and more interconnected than Newton ever dreamed. Yet for all we've uncovered, mysteries remain. Quantum mechanics suggests spacetime might be granular at the tiniest scales, while relativity treats it as smooth. Near a black hole's singularity, where densities reach infinity, these theories collide violently. Unifying them remains physics' greatest challenge, and black holes, the universe's most ruthless laboratories, may hold the key. They're not just cosmic vacuum cleaners, they're windows into the fundamental nature of reality. For decades, black holes were thought to be eternal prisons, cosmic traps where matter and energy entered but never left. Then came Stephen Hawking with a revelation so startling it rewrote astrophysics. Black holes aren't permanent, they leak. In 1974, Hawking proposed that these gravitational giants slowly emit radiation, shedding mass over incomprehensible timescales until they vanish entirely. This phenomenon, now called Hawking radiation, hinges on one of quantum mechanics' strangest quirks, the idea that empty space isn't truly empty. Picture the vacuum of space as a roiling sea of virtual particles, pairs of particles and antiparticles flickering in and out of existence too quickly to be detected. Normally, they annihilate each other instantly, but near a black hole's event horizon, gravity's grip can tear them apart. One particle falls in while the other escapes, stealing a tiny amount of the black hole's energy in the process. To an outside observer, this escaping particle stream looks like faint thermal radiation, a whisper of heat from the universe's coldest places. The implications are staggering. Given enough time, even the mightiest black hole could evaporate, its mass bleeding away into nothingness. Yet this elegant theory comes with a cosmic conundrum, the infamous black hole information paradox. According to quantum mechanics, information about particles can never be truly destroyed. But if a black hole evaporates, what happens to all the data about the stars, gas, and planets it swallowed? Does it vanish forever, violating quantum laws, or is it somehow encoded in the Hawking radiation itself? physicists remain fiercely divided, with some proposing holographic theories where information is imprinted on the event horizon like a cosmic hard drive, while others suggest entirely new physics at play. Hawking's calculations revealed another twist: the smaller the black hole, the faster it evaporates. A typical stellar mass black hole would take longer than the current age of the universe to fade away. But hypothetical micro black holes, if they exist, could explode in a final burst of gamma rays. Though none have been observed, their potential discovery would revolutionize our understanding of quantum gravity. What makes Hawking radiation so profound isn't just its challenge to classical physics, but its bridge between gravity and quantum theory, two frameworks that otherwise refuse to reconcile. It suggests that black holes aren't just celestial vacuums, they're laboratories for the universe's deepest secrets. Every photon they emit carries clues about spacetime's fundamental nature, offering glimpses into a unified theory of everything. For all their darkness, black holes may yet shine light on the cosmos' greatest mysteries. At the heart of our swirling cosmic home, the Milky Way, lies a sleeping giant, Sagittarius, a star. This supermassive black hole, 4 million times heavier than our Sun, anchors our galaxy with its gravitational might, yet behaves remarkably differently from its more active cousins across the universe. Unlike the ravenous quasars blasting energy across billions of light years, Sagittarius, a star, sits relatively quiet, almost demure, at least for now. But its calm exterior hides a violent potential, revealed by the frenetic dance of stars trapped in its gravitational grip. One such star, called S2, has become a key witness to the black hole's power. Orbiting Sagittarius, a star, in a blistering 16-year loop, S2 reaches speeds exceeding 15 million miles per hour at its closest approach, nearly 3% the speed of light. At that velocity, you could circle Earth's equator in under 4 seconds. Astronomers tracked S2's elliptical path for decades using adaptive optics on telescopes like Hawaii's Keck Observatory, watching as its light stretched and reddened under extreme gravity, exactly as Einstein predicted. These observations didn't just confirm the black hole's presence, they gave us front-row seats to relativity in action, where spacetime itself bends under unimaginable force. In May 2022, the Event Horizon Telescope collaboration unveiled another breakthrough, the first ever image of Sagittarius, a star's shadow. Though smaller and dimmer than the previously photographed M87 star, our galaxy's black hole revealed a similar glowing ring of warped light, a fingerprint of its spacetime warping nature. Capturing this image was like photographing a donut on the moon from Earth, requiring global telescope coordination and years of data processing. The result: proof that even our quiet black hole follows the same cosmic rules as its more flamboyant relatives. But Sagittarius, a star's tranquility might be temporary. Infrared and X-ray telescopes occasionally catch it flaring sudden bursts of brightness when stray gas clouds or asteroids wander too close. In 2019, it devoured an unusually large clump of material, glowing 75 times brighter than normal for a few hours. These episodes hint at a turbulent past and future. Some studies suggest our black hole experienced violent feeding frenzies just a few million years ago, lighting up the galactic center like a quasar. The same could happen again when the next dense molecular cloud spirals inward. What's truly remarkable is how Sagittarius, a star, for all its power, doesn't dominate the Milky Way. Unlike galaxies with central black holes millions of times more massive, ours seems perfectly balanced, large enough to organize the stars around it, but not so voracious that it stifles galactic evolution. This equilibrium may explain why life had time to emerge in our quiet corner. As we keep studying this gravitational linchpin, every discovery peels back another layer, revealing how even the most monstrous black holes can shape rather than destroy the delicate conditions that make our cosmic neighborhood home. Imagine two invisible titans waltzing through the void, locked in a death spiral that shakes the very fabric of space-time. This isn't science fiction, it's the reality of black hole mergers, some of the most violent events in the universe. In September 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting ripples in space-time from two black holes colliding over 1 billion light-years away. These gravitational waves, predicted by Einstein a century earlier, revealed a cataclysm so powerful it briefly outshone all the stars in the observable universe combined. The numbers involved are staggering. When black holes merge, they convert a portion of their combined mass into pure energy up to 8% according to simulations. For perspective, the first detected merger between two black holes, each around 30 times the Sun's mass, released more energy in gravitational waves than all the light emitted by every star in the universe during that same fraction of a second. That energy surge warps spacetime itself, sending out ripples that travel at light speed across cosmic distances, stretching and squeezing everything in their path by amounts smaller than an atomic nucleus. Yet LIGO exquisitely sensitive detectors with mirrors suspended by glass threads to isolate them from earthly vibrations caught these subtle tremors, proving that even the faintest cosmic whispers can be heard. What happens during a merger defies imagination. As two black holes orbit each other, they lose energy through gravitational waves, spiraling closer at speeds approaching half the speed of light. In the final milliseconds before collision, their event horizons stretch and distort like taffy before suddenly snapping together, forming a single, more massive black hole. The newborn black hole rings like a bell, vibrating at frequencies that reveal its size and spin, a phenomenon called quasi-normal modes. Meanwhile, any excess energy not absorbed by the new black hole gets blasted outward as gravitational waves, carrying the cosmic fingerprint of the collision. These mergers aren't just spectacular light shows, they're cosmic recycling plants. The resulting black hole can be significantly less massive than the sum of its predecessors, with the missing mass transformed into gravitational wave energy. Some mergers produce black holes in the elusive intermediate mass range between 100 and 100,000 solar masses, a category once thought hypothetical. Others, like the record-setting GW190521 event detected in 2019, challenge our understanding of black hole formation, with progenitor black holes so large they shouldn't exist under conventional stellar evolution models. Perhaps most astonishing is how common these events appear. Since that first detection, LIGO and its European counterpart Virgo have catalogued dozens of mergers, revealing a hidden population of black holes dancing through the darkness. Some collisions involve pairs orbiting for billions of years before finally merging. Others may be the result of chaotic encounters in dense star clusters. Each detection peels back another layer, showing us a universe where black holes aren't just static traps, they're dynamic, evolving creatures, constantly reshaping both themselves and the cosmos around them through these violent embraces. What's next? Future observatories, like the space-based LISA mission slated for the 2030s, will detect mergers between supermassive black holes, events so powerful they could warp spacetime on galactic scales. These collisions may explain how black holes grow to billions of solar masses and whether they truly anchor galaxy formation. Every ripple in spacetime is a message from the universe's darkest corners, reminding us that even in the void, nothing stays still forever. Somewhere between the familiar stellar mass black holes and the gargantuan supermassive ones lurks a cosmic missing link, an enigma that has eluded astronomers for decades. These are intermediate mass black holes, weighing between 100 and 100,000 times the mass of our Sun. Too large to form from a single collapsing star, yet too small to anchor entire galaxies like their supermassive cousins. They occupy a mysterious middle ground that could hold crucial clues about how black holes grow and evolve. Their scarcity in observations isn't due to lack of searching. It's a cosmic detective story with profound implications. The challenge in spotting these elusive objects lies in their nature. Stellar mass black holes reveal themselves through X-rays when they siphon gas from a companion star, while supermassive ones announce their presence with blazing quasars or the frenzied orbits of surrounding stars. Intermediate mass black holes, however, often lurk in isolation with no nearby stars to feed on and no galaxy-scale accretion disks to light them up. They're the cosmic equivalent of a whisper in a hurricane, easily drowned out by the universe's louder phenomena. Yet a handful of tantalizing candidates have emerged. In dense globular clusters like Omega Centauri, astronomers have spotted stars whirling around invisible central masses too hefty for neutron stars but nowhere near supermassive scales. Other hints come from ultraluminous X-ray sources, strange objects pouring out more energy than any known stellar process but less than a quasar's fury. Why does this gap matter? These missing link black holes could be the seeds from which supermassive giants grow. One theory suggests the early universe birthed countless intermediate mass black holes directly from collapsing gas clouds, bypassing the star stage entirely. Over eons, mergers and accretion could have bulked them up into the galactic behemoths we see today. Alternatively, they might form through runaway collisions in packed star clusters, where successive generations of black holes merge like cosmic snowballs. Each scenario leaves distinct fingerprints, chemical imprints on surrounding stars, gravitational wave signals, or patterns in their growth rates that astronomers are only now learning to read. The recent detection of gravitational waves from mergers involving black holes in this elusive mass range has added fuel to the hunt. Events like GW 190521, involving an 85 solar mass black hole colliding with a 66 solar mass partner, defy conventional stellar evolution models. Could these be the remnants of earlier intermediate mass mergers? The answer might rewrite our understanding of how black holes climb the cosmic ladder. What's clear is that finding these hidden middleweights isn't just about completing a classification chart. It's about unraveling the life cycle of black holes themselves. Every candidate discovered peels back another layer, revealing whether supermassive black holes grew from humble beginnings or were born colossal, whether they shaped galaxies or were shaped by them. In the grand tapestry of cosmic evolution, intermediate mass black holes might be the stitches holding everything together, threads we're only now beginning to trace. Black holes don't just consume, they create some of the universe's most spectacular fireworks. While their event horizons famously trap everything that crosses them, these cosmic monsters also blast out jets of matter so powerful they can pierce entire galaxies. Picture a cosmic fire hose spraying particles at over 99% the speed of light, stretching hundreds of thousands of light years across interstellar space. These are relativistic jets, and they're not mere byproducts of a black hole's feast. They're fundamental to how black holes interact with and shape the cosmos around them. The secret behind these blazing beams lies in the chaos surrounding feeding black holes. As matter spirals toward the event horizon, it doesn't plunge straight in. It forms a swirling, superheated disk called an accretion disk, where magnetic fields grow unimaginably strong. These fields twist into corkscrew shapes by the black hole's rotation, channeling some of the infalling particles outward along the poles at nearly light speed. The process resembles water spiraling down a drain, only to get shot back up through two opposing nozzles with enough force to escape the black hole's gravitational clutches entirely. What's astonishing isn't just the speed, it's the precision. These jets often remain tightly collimated over vast distances, barely spreading out as they cross intergalactic space, a testament to the incredible energies involved. The impact of these jets is anything but subtle. When they plow through surrounding gas clouds, they trigger shock waves that can compress matter and ignite new star formation, a cosmic paradox where destruction breeds creation. In other cases, they sterilize entire regions of galaxies, heating interstellar gas so intensely that star formation shuts down for billions of years. The most dramatic examples occur in radio galaxies like Cygnus A, where twin jets slam into intergalactic material, creating colossal lobes that emit radio waves visible across the universe. These structures can outshine their host galaxies by orders of magnitude, turning what would otherwise be invisible black holes into some of the brightest objects in the sky when viewed with radio telescopes. What makes these jets truly fascinating is how they serve as cosmic particle accelerators far more powerful than anything we could build on Earth. The particles within them, mostly electrons and protons, get boosted to energies millions of times higher than those produced in the Large Hadron Collider. When these high-speed particles interact with magnetic fields or photons, they emit light across the spectrum from radio waves to gamma rays, creating beacons detectable across the cosmos. Some scientists speculate that ultra-high-energy cosmic rays, mysterious particles hitting Earth's atmosphere with energies exceeding a thrown baseball, might originate from these black hole jets. Yet mysteries remain. Not all black holes produce jets. Why some do while others don't is still debated. The role of spin is crucial. Rapidly rotating black holes seem more likely to form powerful jets, suggesting their rotation energy gets tapped directly. Even more puzzling is how these jets sometimes flicker or change direction, as if the black hole's nozzle has a mind of its own. Every observation peels back another layer, revealing black holes not as simple vacuum cleaners, but as dynamic engines capable of both destruction and creation on scales that dwarf human comprehension. These jets are reminders that even the darkest objects in the universe can light up the cosmos in ways we're only beginning to understand. Nestled in the heart of a galaxy so large it makes the Milky Way look like a satellite, IC-101's supermassive black hole reigns as the heavyweight champion of our cosmic neighborhood. This titan, lurking 650 million light-years away in the constellation Serpens, tips the scales at an estimated 40 to 100 billion solar masses, making it potentially 20 times more massive than Ton 618's already unfathomable bulk. To grasp its sheer enormity, picture an event horizon so vast that if placed in our solar system, it would swallow everything out past the orbit of Neptune, leaving Pluto and the Kuiper belt as mere crumbs circling an insatiable mouth. Yet IC-101's black hole is shrouded in mystery. Unlike Ton 618, which reveals itself through a brilliant accretion disk visible across billions of light-years, our local giant hides in relative quiet. Astronomers first inferred its presence not by direct observation, but by studying the dizzying orbits of stars near its galaxy's core. These stars whip around at mind-bending speeds, their trajectories betraying the gravitational hand of something monstrously dense. Follow-up studies using the Hubble Space Telescope and ground-based observatories pinned down its staggering mass, confirming it as the most massive black hole within a billion light-years of Earth. What makes IC-101's black hole particularly fascinating is how it reflects its host galaxy's extremes. IC-101 itself is a lenticular galaxy spanning over 6 million light-years, the largest known galaxy by volume, likely grown to such proportions through eons of galactic cannibalism. Its central black hole mirrors this history of excess, possibly bulking up through countless mergers with other black holes during its galaxy's violent expansion. Unlike quasars that blaze with youthful vigor, this elder statesman sits in a more subdued phase, its accretion disk dimmed by time and dwindling fuel supplies. Comparing it to Ton 618 reveals intriguing cosmic diversity. Though Ton 618 outshines its rival with an accretion disk brighter than entire galaxies, IC-101's black hole dominates in raw gravitational might. This difference hints at separate evolutionary paths. Ton 618 may represent a brief, hyperactive phase of black hole growth, while IC101 embodies the culmination of slow, steady accumulation over billions of years. Both redefine our understanding of how large black holes can grow, challenging theories that once placed strict limits on their upper sizes. The study of such giants forces astronomers to rethink fundamental questions. How did IC101's black hole accumulate such mass without blowing away nearby gas with its radiation pressure? Could its calm demeanor suggest a future phase for all supermassive black holes, a quiet senescence after the fiery tempests of youth? Every observation peels back another layer, revealing that even in our cosmic backyard, black holes continue to defy expectations, rewriting the rules of galactic evolution with their sheer gravitational dominance. Crossing the event horizon isn't the only danger when approaching a black hole. Long before you reach that point of no return, its gravity will twist you into an unrecognizable cosmic noodle. This nightmare scenario has a deceptively playful name: spaghettification. It's the brutal stretching and compression caused by tidal forces, the same phenomenon that creates Earth's ocean tides but amplified to horrifying extremes. Picture stepping into a gravitational funhouse mirror where the difference in pull between your head and feet becomes so severe that your body elongates like taffy, thinning out until you're a stream of atoms spiraling toward oblivion. Here's how the physics of this gut-wrenching process works. Tidal forces arise because gravity weakens with distance, meaning your feet, closer to the black hole, get yanked harder than your head. Near smaller black holes, where the event horizon is relatively close to the singularity, this difference becomes catastrophic over very short distances. At just 1,000 kilometers from a stellar mass black hole, the gravitational gradient could be thousands of times stronger than Earth's pull on its oceans. Your body would experience forces equivalent to hanging from a cliff by your ankles while someone tied a freight train to your wrists, except the stretching happens in all directions, compressing your sides while pulling your length into a thinning strand. Astronomers have actually observed this process in action, not with humans, fortunately, but with stars. When a star wanders too close to a supermassive black hole, tidal forces rip it apart in a spectacular event called a tidal disruption flare. The star doesn't go quietly, it's stretched horizontally while being compressed vertically, transforming into a luminous ribbon of plasma before fragmenting into a swirling debris disk. Some of this material gets ejected at relativistic speeds, while the rest spirals inward, emitting X-rays bright enough to spot across billions of light years. These cosmic fireworks serve as real-world demonstrations of spaghettification's destructive power. What's particularly unsettling is how the experience would unfold for an unlucky traveler. Unlike the instantaneous squashing often depicted in movies, spaghettification near a supermassive black hole could take minutes due to its larger event horizon, meaning you'd remain agonizingly aware as your body deformed. Your atoms, stretched beyond molecular bonds, would emit a final burst of radiation, an eerie death knell broadcast to the universe. Even more bizarrely, an outside observer would see your time slow to a crawl near the event horizon, freezing your last moments in a grotesque tableau, while from your perspective, the end would arrive swiftly. This gruesome fate isn't unique to black holes in theory. Any extreme gravitational gradient could cause it. But black holes offer the most dramatic stage for this physics horror show, serving as reminders that the universe isn't just indifferent to human existence, it's capable of unraveling us in ways that defy imagination. As we study these events through telescopes and simulations, we gain more than just morbid curiosities. We uncover fundamental truths about how gravity shapes the cosmos, one stretched star or hypothetical astronaut at a time. Most black holes wear the event horizon like an impenetrable cloak, hiding their singularities from the universe. But what if that cloak could be ripped away? Enter one of astrophysics' most provocative ideas, the naked singularity. These hypothetical cosmic rebels are black holes stripped of their event horizons, exposing their infinitely dense cores to the outside universe. Unlike their modest counterparts, naked singularities would flaunt their extreme physics for all to see, tearing up the rulebook of general relativity in the process. The concept stems from Einstein's equations themselves. Under certain extreme conditions, like a black hole spinning at the absolute limit or inheriting unusual properties from a dying star, the mathematics suggests the event horizon might never form. Instead, you'd get a singularity suspended in plain space-time, gravity's ultimate weapon with no safety shield. Picture a cosmic buzzsaw with infinite density, warping space and time so severely that light could orbit it in bizarre loops before escaping. Unlike normal black holes, where the singularity remains safely hidden behind the event horizon's curtain, naked singularities would broadcast their chaotic physics across the cosmos. This isn't just theoretical whimsy, it challenges one of cosmology's foundational principles, the cosmic censorship hypothesis. Proposed by physicist Roger Penrose, this conjecture acts as a cosmic decorum rule, stating that all singularities must be politely hidden behind event horizons to prevent their infinite densities from wreaking havoc on physics as we know it. Naked singularities laugh in the face of this decorum. If they exist, they'd create regions where predictability breaks down entirely, where time might loop back on itself, and where cause and effect could twist into knots. The hunt for these cosmic rule breakers has turned up tantalizing maybes. Some astronomers scrutinize hyper-energetic cosmic rays for patterns that might betray a naked singularity's fingerprints. Others model extreme gravitational wave signals that could carry traces of horizonless objects. Perhaps most intriguing are certain gamma-ray bursts, explosions so powerful they're visible across the universe, that don't quite fit conventional models. Could a handful of these be the death cries of stars collapsing directly into naked singularities? Yet for all their theoretical allure, naked singularities face fierce skepticism. Many physicists argue that nature abhors such indiscretion, that some undiscovered mechanism always ensures singularities remain clothed. Others counter that the universe might allow these rebels in controlled doses, perhaps only under conditions so extreme they've occurred just a handful of times since the Big Bang. What's undeniable is that the mere possibility of naked singularities forces us to confront the limits of our knowledge, probing where Einstein's equations might fray at the edges and where new physics must take over. Whether cosmic censorship holds or not, the debate itself reveals something profound. Black holes, with or without event horizons, aren't just objects. They're the universe's way of stress-testing our theories, pushing us to ask deeper questions about space, time, and the very nature of reality. In the quest to understand them, we're not just mapping the cosmos, we're discovering where the map itself starts to tear. Black holes aren't just cosmic wrecking balls, they're celestial power stations, capable of energizing entire galaxies with their ferocious output. At the heart of nearly every massive galaxy, supermassive black holes act like gravitational dynamos, converting swallowed matter into colossal bursts of radiation and high-speed jets. This energy doesn't just vanish into the void, it floods surrounding space, heating interstellar gas and dictating where and when new stars can form. Picture a supermassive black hole as the ultimate galactic thermostat, its outbursts alternately stoking or stifling star formation across billions of years. The process begins in the accretion disk, where infalling gas reaches temperatures of millions of degrees, emitting enough X-rays and ultraviolet light to ionize gas clouds thousands of light years away. But the real game changers are the relativistic jets, narrow beams of plasma rocketing outward at nearly light speed. When these jets plow into galactic gas clouds, they create shock waves that can compress matter to trigger star birth in some regions while blasting other areas clean of star-forming material. Astronomers call this push and pull dynamic feedback, And it's why galaxies with actively feeding black holes often exhibit striking patterns of star formation, concentric rings of newborn stars with barren voids in between. One of the most dramatic examples lies in the galaxy cluster MS-735, where a central black hole's jets have carved out vast bubbles in the surrounding hot gas, each cavity large enough to swallow the Milky Way. These bubbles act like cosmic pressure valves, preventing the gas from cooling and collapsing into new stars too rapidly. Without this regulatory mechanism, galaxies might burn through their star-forming fuel in brief, furious bursts, leaving them sterile and lifeless long before intelligent life could emerge. What's truly remarkable is how balanced this system remains over cosmic time. Too much black hole activity sterilizes galaxies prematurely. Too little allows gas to pool unchecked, forming stars so densely that collisions and supernova would render planetary systems uninhabitable. Our own Milky Way strikes this delicate equilibrium. Sagittarius, a star's occasional meals provide just enough feedback to maintain steady star formation without overwhelming the galactic neighborhood. This intricate dance extends beyond individual galaxies. When quasars in the early universe blasted radiation across billions of light years, they may have helped reionize the cosmos, tearing apart hydrogen atoms to make space transparent for future starlight. Black hole outflows also enrich intergalactic space with heavy elements, seeding future generations of stars and planets with the building blocks for life. Far from being mere destroyers, these gravitational giants emerge as architects of cosmic structure, their violent outbursts quietly nurturing the conditions for complexity to arise. Yet mysteries linger. Why do some black holes transition between active and quiescent phases, flipping their feedback on and off like a cosmic switch? How exactly do jets couple with galactic gas to produce such finely tuned regulation? Each telescope observation and supercomputer simulation peels back another layer, revealing black holes not as isolated monsters, but as the beating hearts of galactic ecosystems pulsing with energy that shapes everything from stellar nurseries to the possibility of life itself. Deep in the constellation grooves, a cosmic glutton shatters all records. J2157, the fastest-growing black hole ever discovered. This ravenous beast devours the equivalent of an entire sun's worth of mass every single day, swelling at a rate that defies belief. To put that in perspective, if our Milky Way Sagittarius a star ate at the same pace, it would consume 400,000 Earth masses daily, transforming entire planets into a fleeting snack. J2157 isn't just big, it's expanding at the theoretical limit of how fast a black hole can gorge itself, a frenzy that's rewriting our understanding of these cosmic predators. Astronomers first spotted this monster in 2018 using the SkyMapper telescope in Australia, its brilliance standing out even from 12.5 billion light-years away. What caught their eye wasn't the black hole itself, it was the quasar's dazzling glow, fueled by the superheated gas spiraling into its maw. The numbers stunned researchers, 34 billion times the sun's mass already, with a growth rate so voracious that its event horizon stretches wider than our entire solar system. Every second, enough matter to fill 300,000 Earths vanishes beyond its point of no return, releasing energy equivalent to 1 trillion nuclear explosions. What makes J2157 truly extraordinary isn't just its appetite, it's the window it provides into the universe's most extreme feeding mechanisms. Most supermassive black holes, like our galaxies, snack intermittently on passing gas clouds, but this one behaves like it's at an all-you-can-eat cosmic buffet, gorging non-stop for billions of years. The secret lies in its environment. J2157 likely inhabits a galaxy crammed with dense gas clouds, creating a perfect storm of endless fuel. As material funnels inward, friction heats it to millions of degrees, creating a luminous beacon visible across the cosmos. Yet such unchecked gluttony raises profound questions. According to classical physics, there's a speed limit to black hole growth, the Eddington limit, where radiation pressure from the infalling matter should blow away surrounding gas, cutting off the food supply. J2157 blows past this limit, suggesting either our models are incomplete or we're witnessing a rare super Eddington phase where gas falls inward faster than radiation can push it back. Some theories propose magnetic fields help funnel material past the barrier, like cosmic straws bypassing the usual rules. This insatiable giant also offers clues about the early universe's most violent epochs. Its light reaches us from when the cosmos was just 1.2 billion years old, a mere toddler by cosmic standards. How did a black hole grow so massive so quickly? One possibility is direct collapse, where primordial gas clouds skip the star phase entirely, collapsing straight into black holes thousands of times the sun's mass. These seeds could then merge and feast, bulking up to J2157 staggering proportions while the universe was still in diapers. Every observation peels back another layer of mystery. Will this black hole eventually exhaust its fuel and dim like modern quasars? Or does it represent a bygone era when the universe's fattest giants dined without restraint? For now, J2157 stands as both a cosmic anomaly and a Rosetta Stone, its outrageous appetite teaching us that even the universe's most extreme rules have exceptions waiting to be uncovered. Around a black hole's event horizon lies one of the most bizarre optical illusions in the universe, a shimmering ring of trapped light known as the photon sphere. Imagine a cosmic carousel where beams of light, instead of escaping or falling in, circle the black hole endlessly like riders stuck on a celestial merry-go-round. This twilight zone forms at exactly 1.5 times the distance of the event horizon, a region where gravity warps space-time so severely that photons travel in perfect loops, neither plunging inward nor breaking free. Under the right conditions, these trapped photons create a halo around the black hole, a ghostly ring that defies everything we know about how light should behave. The physics behind this eerie phenomenon hinges on Einstein's theory of general relativity. Light, which normally travels in straight lines, follows the curves of warped spacetime near a black hole. At the photon sphere's precise distance, spacetime bends so sharply that light's path becomes a closed orbit. Some photons spiral inward after multiple loops, while others escape to reach our telescopes, creating the illusion of a luminous ring embedded in the black hole's shadow. This effect was famously captured in the Event Horizon Telescope's image of M87's supermassive black hole, where the bright accretion disk's light bent around the void, forming a perfect circle of fire. What makes photon spheres more than just cosmic curiosities is what they reveal about black holes themselves. The size and shape of this light ring depend entirely on the black hole's mass and spin, meaning observing it can help astronomers measure these properties with unprecedented precision. A fast-spinning black hole, for instance, distorts the photon sphere into an oblong shape, while a static one keeps it perfectly spherical. Some theoretical models even suggest that multiple photon rings could exist, nested like Russian dolls, each corresponding to light that orbited the black hole different numbers of times before escaping. These subtle variations encode a wealth of data about the black hole's history and behavior. Yet the photon sphere isn't just a passive observer's tool, it's a battlefield for fundamental physics. Quantum mechanics suggests that photons trapped here could interact in strange ways, their paths perturbed by virtual particles popping in and out of existence near the event horizon. Some theories propose that these interactions might subtly alter the ring's properties over time, offering clues about how gravity and quantum mechanics reconcile in extreme environments. For all its delicate beauty, the photon sphere is a place of chaos, where the universe's most basic rules are stretched to their breaking point. Perhaps the most mind-bending implication is what the photon sphere would look like to a hypothetical observer nearby. Stand just outside this boundary, and you'd witness light from every direction bent into a swirling vortex, the entire universe compressed into a dazzling band encircling the abyss. Behind you, the stars wouldn't just twinkle, they'd smear into distorted arcs, their light bent into impossible geometries by the black hole's grip. This isn't science fiction, it's the unvarnished reality of how gravity twists reality itself. The photon sphere doesn't just illuminate black holes, it forces us to confront how deeply twisted spacetime can become when pushed to its limits. Long before stars and galaxies existed, in the searing chaos of the early universe, space itself may have birthed black holes unlike any we see today. These are primordial black holes, cosmic relics thought to have formed not from collapsing stars, but from the extreme density fluctuations in the first fraction of a second after the Big Bang. Picture the newborn universe as a bubbling cauldron of space-time, where pockets of matter could have collapsed directly into black holes with masses ranging from a speck of dust to thousands of suns. Unlike their stellar-born cousins, these ancient anomalies wouldn't need a star's death throes to exist. They'd be fossils from creation itself, lurking unseen for over 13 billion years. What makes primordial black holes so compelling isn't just their origin story, it's the tantalizing possibility that they might solve one of astronomy's greatest mysteries, dark matter. If enough of these ancient objects formed and survived, they could account for the invisible mass binding galaxies together. Some theories suggest a universe teeming with asteroid-sized primordial black holes, each weighing as much as a mountain, drifting through space like invisible icebergs. Their collective gravity could explain why galaxies rotate faster than visible matter alone should allow, without invoking exotic particles. It's an elegant solution. Dark matter might not be a strange, unknown substance, but ordinary matter locked away in black holes forged at the dawn of time. Yet for all their theoretical promise, primordial black holes remain frustratingly elusive. Their predicted sizes make direct detection nearly impossible. Small ones would have evaporated via Hawking radiation by now, while larger ones are too sparse to spot easily. Astronomers have searched for their fingerprints everywhere, in subtle distortions of starlight, unexplained gamma-ray bursts, even the ripples they'd create in cosmic background radiation. The lack of definitive evidence has led some to dismiss them, while others argue we've barely scratched the surface of possible detection methods. The hunt gained new urgency with gravitational wave observatories like LIGO. Some of the black hole mergers it's detected involve objects too massive to form from typical stellar collapse. Could these be primordial black holes finally revealing themselves? Others point to bizarre microlensing events, where stars momentarily brighten as unseen objects pass in front of them as potential clues. The math suggests primordial black holes would leave a distinct statistical signature in these events, though current data remains inconclusive. Perhaps the most mind-bending implication is that some primordial black holes could still be with us today. Those between 1 and 1,000 solar masses too large to have evaporated, too small to anchor galaxies, might wander the cosmos undetected, occasionally colliding with stars or planets. Some theorists have even speculated that one could have captured primordial gas to form a hidden, black hole star with a dark heart. Whether these ideas hold up or not, the mere possibility reshapes how we view the universe's inventory of darkness. The search for these cosmic elders forces us to confront profound questions. Did the Big Bang leave behind a hidden population of gravitational traps? Are we surrounded by ancient black holes without realizing it? Every null result narrows the possibilities, while every anomalous observation reignites the debate. Primordial black holes embody one of science's most thrilling pursuits, the quest to uncover relics from the universe's first moments, hiding in plain sight. Black holes might not just be cosmic endpoints, they could be the birthplaces of entirely new universes, hidden within their crushing depths. This mind-bending idea, first proposed by physicist Lee Smolin, flips our understanding of black holes on its head. Instead of being mere destroyers, they become creators' mathematical gateways where space-time folds in on itself so intensely that it triggers a new Big Bang. Picture a Russian nesting doll of universes, each black hole in our cosmos containing a fledgling universe of its own, with its own laws of physics and perhaps even its own black holes spawning yet more universes in an infinite cascade. Smolin's theory of cosmological natural selection takes this even further. He suggests that universes could evolve through a form of cosmic Darwinism, where black hole births favor the conditions that produce more black holes. In this scenario, universes that fine-tune their physical constants like the strength of gravity or the mass of electrons to maximize black hole production would reproduce more prolifically. Over countless generations, this could explain why our universe seems so finely tuned for black hole formation. It's a radical answer to one of physics' biggest questions. Why do the fundamental constants of nature appear so perfectly calibrated for complexity to arise? The mechanics behind this universe-spawning process hinge on the extreme physics near a black hole singularity. As matter collapses beyond the event horizon, some theories suggest quantum gravitational effects could become so dominant that they halt the collapse and trigger a bounce, inflating a new spacetime bubble detached from our own. This baby universe would inherit some properties from its parent, but might develop wildly different physical laws like a cosmic mutation. Some models even propose that the singularity isn't a point of infinite density but a bridge to another spacetime, a concept echoing the wormholes of science fiction but grounded in the equations of general relativity. Not everyone embraces these ideas. Critics argue that without observable evidence, they remain in the realm of metaphysics. How could we ever detect a universe inside a black hole when no information escapes? Others counter that subtle fingerprints might exist anomalies in cosmic microwave background radiation, unexplained gravitational wave signatures, or statistical oddities in black hole distributions. The search is complicated by the fact that these theories often require extensions to known physics, like loop quantum gravity or string theory, which themselves await experimental confirmation. What's undeniable is how these speculations stretch our imagination. If true, every black hole could be a cosmic matryoshka doll, its interior hosting an entire cosmos unseen and unreachable from our perspective. Our own universe might then be the descendant of a black hole in some higher dimensional parent universe, part of an unending chain of cosmic reproduction. Whether this vision holds up or not, it reminds us that black holes aren't just dead ends, they're windows into the most profound questions about existence itself, challenging us to rethink where universes come from and where they might ultimately lead. Not all black holes rage with the fury of quasars or blaze with the glow of accretion disk. Some slumber in near silence, their monstrous appetites temporarily sated. These dormant giants, like our own Sagittarius, a star, prove that supermassive black holes don't disappear when they stop feeding. They simply bide their time, lurking in galactic cores like hibernating bears. Their quiet periods offer just as much insight as their active phases, revealing how these cosmic predators cycle between rest and riot. What puts a black hole to sleep? The answer lies in its cosmic pantry. Black holes shine brightly when they consume gas, dust, or stars, but when that supply runs low, their accretion disks dim to near invisibility. Sagittarius, a star, for instance, sits in a relatively gas-poor region of the Milky Way center, where most nearby matter already orbits at safe distances. Without fresh material spiraling inward, the black hole enters quiescence, emitting only faint flickers of X-rays as it nibbles on the occasional asteroid or wisp of interstellar gas. Even its event horizon becomes eerily still, absent the violent distortions seen in feeding black holes. But dormancy isn't permanent. Like a volcano between eruptions, these quiet giants can awaken with terrifying speed when new fuel arrives. In 2019, Sagittarius, a star, briefly flared 75 times brighter than normal after consuming a rogue gas cloud, a snack that lasted mere hours, but revealed how quickly even a placid black hole can switch to feast mode. Larger disruptions, like a star passing too close, can trigger years-long outbursts, shredding the star into a luminous tidal disruption flare. These awakenings aren't random. They follow the rhythm of galactic dynamics, where passing molecular clouds, colliding star clusters, or even smaller black holes on chaotic orbits can suddenly refuel the dormant beast. The contrast between active and quiescent black holes reshapes our understanding of galactic evolution. In denser galaxies where gas clouds crowd the core, supermassive black holes may spend more time in active phases, their radiation and jets sculpting star formation across light years. In quieter galaxies like ours, they dominate through gravity rather than glare, their subtle tugs on orbiting stars betraying their presence. Some theorists suggest these cycles regulate galaxy growth. Too much activity blows away gas and stifles star birth, while periods of quiet allow new stellar nurseries to form. Dormant black holes also offer unique research opportunities. Without blinding accretion disks, astronomers can study the subtle effects of extreme gravity on nearby stars, testing Einstein's predictions with unparalleled precision. The star S2's orbit around Sagittarius, a star, for example, provided the first direct evidence of gravitational redshift near a supermassive black hole, a key validation of general relativity. Quiet periods also let telescopes peer closer to the event horizon, mapping spacetime's warping without the interference of superheated plasma. Yet mysteries linger. Why do some black holes, like Andromeda's, remain anomalously quiet despite ample gas supplies? Could magnetic fields or unseen jets be diverting material away? And how often do truly monstrous black holes awaken? Could our Milky Way's core one day blaze like a quasar? Each observation peels back another layer, revealing that even in their stillness, these giants hold the keys to understanding the universe's most violent and delicate balances. Black holes don't just devour light, they twist it into cosmic mirages, bending the very fabric of reality to create nature's most powerful telescopes. This phenomenon, called gravitational lensing, occurs when a black hole's immense gravity warps spacetime so severely that it distorts the path of light passing nearby. Picture a beam of starlight traveling toward Earth. If a black hole lies directly in its path, the light doesn't just vanish. Instead, it curves around the black hole like water flowing around a boulder in a stream, creating multiple, stretched, or even ring-shaped images of the original star. It's as if the universe itself has become a funhouse mirror, with black holes as the ultimate illusionists. One of the most striking examples of this cosmic trickery unfolded in 2019, when astronomers observed a star named Icarus amplified over 2,000 times its normal brightness. A black hole in a foreground galaxy had bent the star's light like a magnifying glass, an effect called microlensing. But unlike typical gravitational lenses, which involve entire galaxies or clusters, this extreme magnification revealed the finer details of how solitary black holes warp spacetime on smaller scales. Similar distortions occur when quasars, distant galaxies with active supermassive black holes, appear as multiple images in the sky, their light split and twisted by intervening black holes or dark matter. Gravitational lensing isn't just a celestial curiosity, it's one of astronomy's most powerful tools. By measuring how black holes bend light, scientists can map their mass distribution with precision, even identifying invisible, rogue black holes drifting between stars. The Hubble Space Telescope has captured dozens of these distorted cosmic snapshots, including Einstein rings, perfect circles of light formed when a distant galaxy aligns perfectly behind a massive black hole. These rings aren't just beautiful, they're cosmic scales, letting astronomers weigh black holes by how severely they warp the light passing through their gravitational field. What makes this phenomenon truly remarkable is how it probes the very nature of gravity itself. The exact shape and brightness of lensed images test Einstein's predictions under extreme conditions, revealing whether general relativity holds up near a black hole's event horizon. Some theorists even use subtle anomalies in lensing patterns to hunt for exotic physics, like quantum gravity effects or hidden dimensions. Every distorted quasar or stretched galaxy serves as a natural laboratory, where the universe's most mysterious objects reveal their secrets not by the light they emit, but by how they sculpt the light of others. Perhaps the most poetic aspect of gravitational lensing is how it transforms destruction into creation. A black hole, often seen as the ultimate end for matter and energy, becomes an accidental artist, painting the cosmos with warped light and ghostly rings. These illusions remind us that even in darkness, there's a strange kind of vision, one that lets us see the invisible forces shaping the universe. At the edge of observable time, when the universe was still shaking off the afterglow of the Big Bang, a beacon of destruction already blazed with the fury of a trillion suns. Euler's J1342 plus 0928 isn't just the oldest black hole we've discovered, it's a cosmic anomaly that defies our understanding of how these monsters grow. This quasar, its light reaching us from when the universe was a mere 690 million years old, houses a black hole weighing 800 million solar masses. Wrap your mind around that an object nearly as massive as our Milky Way's central black hole existed when the cosmos was less than 5% its current age, a toddler already wielding the strength of a titan. How does a black hole grow so large so quickly? Conventional models of black hole formation can't explain it. A stellar mass black hole, born from a dying star, would need to gorge on matter at impossible rates for billions of years to reach such sizes. Euler's J1342's existence suggests alternative pathways, perhaps direct collapse black holes, where primordial gas clouds in the early universe skipped the star-forming stage entirely, collapsing directly into black holes thousands of times the sun's mass. These seeds would have a head start, feasting on the dense, pristine hydrogen filling the young cosmos. Others propose runaway mergers in crowded star clusters, where successive generations of black holes slam together like cosmic snowballs, rapidly building mass through violent collisions. What makes this ancient quasar even more astonishing is its environment. The universe at this epoch was just emerging from the cosmic dark ages, the period before the first stars and galaxies fully ionized the fog of neutral hydrogen filling space. Yet Euler's J1342's brilliant accretion disk had already carved a bubble of transparency around it, its ultraviolet radiation stripping electrons from atoms in a process called reionization. This black hole wasn't just feeding, it was helping sculpt the universe's very structure, transforming opaque space into the transparent void we see today. The discovery, made in 2017 using data from the WISE spacecraft and ground-based telescopes, pushed our observational limits to their breaking point. Detecting such a distant object required searching for the subtle redshift of its light, stretched by cosmic expansion into the infrared amid thousands of closer galaxies. Its spectrum revealed another surprise. The gas around it was already enriched with heavy elements like carbon, suggesting star formation had been underway for millions of years before the quasar ignited. This paints a picture of a universe that got busy fast-forming stars, galaxies, and monster black holes in what seems like a cosmic blink, yet mysteries remain. Did Euler's J1342 represent a rare fluke, or were such giants common in the early universe? Future telescopes like the James Webb Space Telescope aim to find more of these ancient leviathans, probing whether they were outliers or part of a hidden population that shaped cosmic dawn. Every answer only leads to deeper questions. How did the first black holes form before galaxies matured to feed them? Could they have influenced galaxy formation rather than the other way around? Euler's J1342 stands as both a revelation and a challenge. forcing us to reconsider the timeline of cosmic evolution and the raw, unfathomable power lurking in the universe's earliest moments. Black holes might seem like the ultimate voids nothing escapes, not even light, but some harbor invisible forces that rival their gravitational might. These cosmic powerhouses can generate magnetic fields trillions of times stronger than Earth's, turning them into dynamic engines rather than simple destroyers. Picture a black hole as a colossal dynamo, where swirling plasma in its accretion disk acts like a cosmic conductor, spinning charged particles into a frenzy and amplifying magnetic fields to unimaginable intensities. These fields don't just linger quietly, they shape some of the universe's most violent phenomena, from relativistic jets that pierce galaxies to the very structure of the black hole's feeding process. The discovery of black hole magnetic fields came not from seeing the fields themselves, but from their fingerprints on the chaos around them. Telescopes like the Event Horizon Telescope and the Chandra X-ray Observatory have spotted telltale signs: polarized light spiraling in distinctive patterns from accretion disks, or jets of particles aligned with eerie precision, as if guided by invisible cosmic rails. In 2021, observations of the supermassive black hole in galaxy M87 revealed magnetic fields so powerful they can slingshot particles to near light speed, creating the jet visible across 55 million light-years. These fields twist and snap like rubber bands, storing vast amounts of energy before releasing it in bursts that ripple through the surrounding galaxy. What's astonishing is how these magnetic fields mastermind the black hole's most dramatic performances. Without them, jets wouldn't form with such razor-sharp focus. As matter spirals toward the event horizon, magnetic field lines act like cosmic particle accelerators, channeling some of the infalling material outward along the black hole's poles instead of inward toward oblivion. This process, called the Blandford-Zenagic mechanism, converts the black hole's rotational energy into focused beams of plasma, nature's version of a railgun firing relativistic projectiles across intergalactic space. The fields also regulate the black hole's appetite, controlling how quickly gas from the accretion disk can fall inward, like a magnetic valve on a cosmic pressure cooker. Yet mysteries remain. Why do some black holes, like Sagittarius, a star, have relatively weak magnetic fields, while others, like those powering quasars, generate fields strong enough to reshape entire galaxies? Some theories suggest the difference lies in the stability of their accretion disks. Chaotic, turbulent disks may amplify fields more efficiently. Others propose that mergers between black holes could temporarily supercharge their magnetic properties, like crashing electrical storms in space. Every new observation peels back another layer, revealing that black holes aren't just gravitational pits, they're electromagnetic maestros, orchestrating cosmic fireworks with forces we're only beginning to measure. These magnetic monstrosities challenge our understanding of physics itself. Near the event horizon, magnetic fields might even warp space-time in ways that blur the line between gravity and electromagnetism, creating conditions where familiar laws break down. Future telescopes like the Square Kilometre Array aim to map these fields in unprecedented detail, probing how they influence everything from star formation to the fate of galaxies. The more we learn, the clearer it becomes. A black hole's true power isn't just in what it destroys, but in what it magnetizes, accelerates, and hurls back into the cosmos with breathtaking force. In the silent void of space, black holes don't just warp the cosmos, they compose a haunting symphony we've only just learned to hear. When two black holes spiral toward collision, they don't explode in a grand burst of light. Instead, they send tremors through space-time itself, gravitational waves that ripple outward at the speed of light. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, captured these waves for the first time, but they didn't stop there. They translated this cosmic vibration into sound, giving humanity its first chance to listen to the universe's darkest embrace. the result is an eerie chirp, a fleeting, ascending tone lasting barely a second. It begins as a low hum, rising in pitch and intensity before abruptly cutting off. That chirp marks the moment the two black holes merge, a crescendo of warped spacetime. To create this sound, researchers took the gravitational wave signal, a distortion smaller than 1/10,000th the width of a proton, and shifted it into the range of human hearing. What you're hearing isn't just artistry, it's real data, a direct sonification of the universe's fabric twisting under unimaginable force. But this chirp isn't just a cosmic curiosity, it's packed with scientific meaning. The pitch reveals the black hole's masses. Heavier pairs produce deeper tones, while lighter ones create higher frequencies. The duration of the signal tells us how long they took to merge, and the abrupt stop signals the formation of a new black hole, ringing momentarily before settling into silence. Each nuance carries clues about the collision's location, the black hole's spins, and even the shape of spacetime itself. It's as if the universe left us a voicemail whispering secrets about its most violent encounters. The most remarkable part, these sounds aren't rare. Since that first detection, LIGO and its European counterpart, Virgo, have captured dozens of these cosmic chirps, each with its own unique fingerprint. Some are quick and sharp, like a rapid drumbeat, evidence of smaller black holes merging in a fraction of a second. Others are drawn out and resonant, tracing the slow dance of behemoths billions of times the sun's mass. Together, they form a growing catalogue of black hole collisions, revealing a hidden population of these dark objects weaving through the cosmos. Listening to these gravitational waves does more than satisfy curiosity, it reshapes how we explore the universe. Traditional astronomy relies on light, but black holes, by their very nature, emit none. Gravitational waves bypass that limitation, offering a new sense, like suddenly gaining the ability to hear after relying solely on sight. Future observatories, like the space-based LISA mission, will detect lower frequency waves, allowing us to hear even larger mergers, the slow, thunderous collisions of supermassive black holes that anchor galaxies. What's next? Scientists are already training AI to sift through noise for fainter chirps, hoping to catch whispers from the universe's first black holes or even exotic objects we've yet to imagine. Every signal peels back another layer, proving that even in the vacuum of space, silence is an illusion. The cosmos thrums with vibrations, and black holes, it turns out, have voices. We're just beginning to decode their songs. Black holes might anchor galaxies with their gravitational might, but even these cosmic titans aren't immune to the universe's violent forces. When two black holes spiral into each other and merge, the collision doesn't always leave the newly formed behemoth sitting quietly at the center of its galaxy. Instead, the explosive union can launch it into exile, a phenomenon astronomers call a gravitational kick. Picture a cosmic cannon firing a black hole at speeds reaching thousands of miles per second, fast enough to escape its galaxy entirely and wander the void between galaxies forever. The physics behind this dramatic ejection hinges on the asymmetry of the merger. When black holes collide, they don't just combine their masses, they unleash gravitational waves, ripples in spacetime that carry energy and momentum away from the system. If the merger isn't perfectly balanced, say, if the black holes have unequal masses or spins, those waves erupt more powerfully in one direction than the other. The result, a recoil effect like a gun firing backward, propelling the merged black hole in the opposite direction. Some kicks are gentle, nudging the black hole into an eccentric orbit. But in extreme cases, the recoil can reach speeds over 5,000 kilometers per second, enough to overcome even the gravitational pull of a galaxy's core. Astronomers have spotted evidence of these runaway black holes streaking through intergalactic space. In 2012, Hubble detected a supermassive black hole racing away from its host galaxy at over 7 million kilometers per hour, trailing a wake of young stars torn from their birthplace. Another candidate, 3 billion light-years away, showed a quasar, a bright beacon powered by an active black hole completely disconnected from any visible galaxy, likely ejected in an ancient merger. These rogue black holes don't travel entirely alone. Some drag clusters of stars with them, ghostly remnants of their former homes. What happens to a galaxy after losing its central black hole? The consequences could be profound. Supermassive black holes regulate star formation and galactic structure, so their absence might leave galaxies unstable, either spawning stars too rapidly or stagnating without the feedback that keeps gas clouds in check. Some theorists even suggest these ejected giants could seed black holes in smaller galaxies they encounter, like cosmic colonists spreading gravitational influence across the universe. Yet the most fascinating aspect of these gravitational kicks is what they reveal about the chaos of black hole mergers. The forces at play are so immense they can fling objects millions of times the sun's mass into the abyss, proof that even the universe's most dominant structures aren't immune to cosmic upheaval. Every rogue black hole discovered peels back another layer, showing us a universe where nothing, not even spacetime's darkest pits, stays in place forever. While supermassive black holes dominate galactic centers with masses spanning millions of suns, their stellar mass cousins prove that cosmic monsters come in smaller, yet equally terrifying packages. These black holes, born from the explosive deaths of massive stars, pack all that gravitational fury into a space no wider than a city. Picture a star 20 times heavier than our sun collapsing under its own weight, its outer layers blasted away in a supernova so violent it briefly outshines entire galaxies while its core crushes down to an infinitesimal point, warping spacetime into an inescapable prison. The result, a stellar mass black hole typically ranging from 3 to 100 solar masses, compacted into a sphere just 30 kilometers across. Small enough to fit inside the length of Manhattan, yet powerful enough to shred any star that strays too close. Detecting these cosmic piranhas requires different techniques than spotting their supermassive counterparts. Since they don't actively feed on galactic-scale gas clouds, stellar mass black holes reveal themselves through X-ray flashes as they siphon material from companion stars. The most famous example, Cygnus X1, was discovered in 1964 as the first strong candidate for a black hole, a celestial stalker orbiting a blue supergiant star, its gravity stealing gas that heats to millions of degrees before vanishing past the event horizon. This stolen matter forms a swirling accretion disk so hot it emits X-rays detectable across the Milky Way, like a cosmic burglar caught in a security camera's infrared glow. What makes stellar mass black holes particularly fascinating is their violent diversity. Some, like V404 Cygni, erupt in unpredictable X-ray flares as clumps of stellar material plummet inward chaotically. Others, like JRO-J1655-40, fire relativistic jets at 90% light speed, proving that even small black holes can unleash cosmic fireworks. Then there's the mysterious GW190521, a black hole so heavy it defied stellar evolution models when LIGO detected its collision in 2019. At 85 solar masses, it shouldn't exist under conventional theories, suggesting either gaps in our understanding or the presence of exotic formation pathways like primordial origins or repeated mergers. Yet these smaller black holes aren't just scaled-down versions of supermassive ones, they're crucibles for extreme physics. Their tighter event horizons mean tidal forces near them are exponentially more severe. While you'd have hours to cross a supermassive black hole's horizon before spaghettification, a stellar mass black hole would shred you in microseconds. Their rapid spins, often approaching light speed, twist nearby spacetime into knots, creating particle acceleration environments unmatched by any human-built collider. Some even serve as natural laboratories for quantum gravity, where the interplay between general relativity and quantum mechanics might leave detectable traces in their X-ray emissions. The study of stellar mass black holes isn't just about cataloging cosmic curiosities, it's a window into stellar life cycles, galactic chemistry, and the universe's most fundamental forces. Every X-ray burst, every gravitational wave chirp, adds another piece to the puzzle of how matter behaves under conditions we can never replicate on Earth. From Cygnus X1's pioneering discovery to the growing menagerie of mergers spotted by LIGO, these compact killers remind us that darkness comes in all sizes, and sometimes the most violent things in the universe come in the smallest packages. Black holes don't just swallow matter, they threaten to erase the very fabric of reality itself. At the heart of this cosmic crisis lies the black hole information paradox, a puzzle so profound it challenges our understanding of physics at its core. The problem starts simply enough. When an object falls into a black hole, it vanishes beyond the event horizon, seemingly lost forever. But here's the catch: quantum mechanics insists that information about that object's state can never truly disappear. This clash between gravity's ruthlessness and quantum theory's ironclad rules has divided physicists for decades, with implications that could rewrite the laws of the universe. Imagine tossing a book into a fire. The pages burn, but in principle, every bit of information, every word, every ink molecule could theoretically be reconstructed from the ashes and smoke. Quantum mechanics operates on this same principle. Information might transform, but it's never destroyed. Black holes throw a wrench into this idea. Once something crosses the event horizon, it's crushed into the singularity, leaving no trace of its original form. Even if the black hole eventually evaporates via Hawking radiation, that radiation appears random, carrying no fingerprints of what fell in. It's as if the universe's hard drive has been wiped clean, violating one of quantum theory's most sacred tenets. Stephen Hawking first spotlighted this paradox in the 1970s, arguing that black holes truly do erase information. His stance sparked a decades-long debate, with opponents like Leonard Susskind countering that this would undermine the foundation of quantum physics. The stakes couldn't be higher. If Hawking was right, we'd need a radical overhaul of how we understand reality. If not, we're missing something fundamental about how black holes work. One compelling solution comes from holographic theory. The idea that all the information swallowed by a black hole isn't lost but encoded on its event horizon like a cosmic fingerprint. Picture the horizon as a two-dimensional hologram storing a perfect record of everything that fell inside, much like how a DVD's flat surface encodes a three-dimensional movie. When the black hole evaporates, this information could theoretically be released, preserving the universe's quantum rulebook. Supporting this wild idea are calculations showing the horizon's surface area, not its volume, determines a black hole's entropy, a hint that information might indeed be stored there. Yet mysteries linger. How exactly does information escape during evaporation? Some theories propose it's scrambled into Hawking radiation like a cryptographic puzzle. Others suggest black holes might have soft hair, low-energy quantum fuzz around their horizons that preserves data. The debate remains fiery, with experiments still beyond our reach. But the paradox isn't just academic. It's a battleground for unifying quantum mechanics and general relativity, a crucial step toward the long-sought theory of quantum gravity. What makes this puzzle so thrilling is how it forces us to confront the limits of our knowledge. Black holes, once thought to be simple destroyers, might actually be the universe's most sophisticated archivists, hiding secrets in ways we're only beginning to imagine. Every new equation, every thought experiment peels back another layer, revealing that even in the darkest corners of space, information, the bedrock of reality, finds a way to endure. Among the most unexpected roles a black hole can play is that of cosmic cartographer, a gravitational lighthouse helping astronomers chart the vast expanse of the universe. While their destructive reputation precedes them, these space-time warps serve as critical reference points for measuring distances across billions of light-years. Imagine a black hole not as a vacuum but as a fixed point in the cosmic grid, its extreme gravity bending light in predictable ways that reveal the universe's hidden architecture. One of their most valuable applications comes from Quasars' supermassive black holes blazing with the light of their accretion disks. Because quasars are among the brightest and most distant objects in the universe, their positions provide a scaffold for three-dimensional maps of cosmic structure. Astronomers use them like surveyor's stakes, plotting the distribution of matter across the largest scales. The Sloan Digital Sky Survey, for instance, has catalogued over 1 million quasars, tracing the cosmic web's filamentary threads where galaxies cluster along invisible lines of dark matter. Each quasar's redshift, how much its light has stretched as the universe expands, acts as a mileage marker, letting scientists reconstruct the universe's expansion history with precision. But black holes don't just help map the cosmos, they refine how we measure it. When two black holes collide, the gravitational waves they produce serve as standard sirens, a term coined because their waveforms reveal the merger's distance without relying on traditional cosmic yardsticks. By comparing these wave-based distances to redshift measurements, astronomers can independently verify the universe's expansion rate, resolving discrepancies in values obtained by other methods. This technique gained fame in 2017 when the merger of two neutron stars provided the first such calibration, but black hole mergers now contribute routinely, adding data points to refine our cosmic ruler. Looking ahead, black holes might even guide interstellar navigation. Proposed missions like NASA's conceptual X-ray navigation system, called XNav, would use pulsars, rapidly spinning neutron stars that behave like cosmic lighthouses, but supermassive black holes could play a similar role. Their predictable X-ray flickers and stable positions make them ideal reference points for spacecraft venturing beyond the solar system, offering a GPS-like system anchored to the universe's most permanent fixtures. Picture future explorers triangulating their position using the steady pulses of Sagittarius, a star, and distant quasars, turning destruction into direction. What makes this role so astonishing is how it inverts expectations. Black holes, often seen as the ultimate endpoints, become starting points, fixed markers in an expanding universe. Whether through gravitational lensing that magnifies faraway galaxies, or as backdrops for measuring dark energy's influence, they've become indispensable tools for decoding cosmic geography. The same gravity that tears stars apart also stitches together our understanding of spacetime's grand design, proving that even the darkest objects can illuminate the universe's deepest mysteries. The next decade promises to revolutionize black hole astronomy with groundbreaking missions poised to peel back the event horizon's secrets like never before. Leading the charge is LISA, the Laser Interferometer Space Antenna, a fleet of 3 spacecraft launching in the 2030s to form a gravitational wave detector spanning millions of kilometers. Unlike Earth-based observatories limited by seismic noise, LISA will orbit the Sun, capturing low-frequency ripples from collisions between supermassive black holes with masses billions of times our Sun's. Picture tuning into the universe's base notes the slow, thunderous mergers of galactic titans that shape the cosmos's large-scale structure. These waves carry fingerprints of black hole spins, orbits, and even the space-time warps around them, offering data no telescope could collect. Meanwhile, the Event Horizon Telescope, the global array that brought us the first black hole image, is expanding its vision dramatically. With new antennas in Africa, Greenland, and space-based components on the drawing board, its next iteration could achieve resolution sharp enough to spot individual photon rings, the nested light circles formed by photons looping a black hole multiple times before escaping. Imagine mapping spacetime's warping like tree rings, counting light orbits to measure a black hole's spin with unprecedented precision. Future upgrades might even track real-time changes in accretion disks, catching flares as stars are torn apart or gas clouds spiral toward oblivion. But the most tantalizing frontier lies in multi-messenger astronomy, combining gravitational waves, light, and even neutrino detection to dissect black holes from every angle. When LISA senses a distant supermassive merger, telescopes across the electromagnetic spectrum could hunt for accompanying flashes, much like the neutron star collision observed in 2017. Such coordinated efforts might finally crack enduring mysteries. Do mergers launch relativistic jets? How do magnetic fields behave during these cosmic crashes? The answers could rewrite textbooks on galaxy evolution and high-energy physics. On the theoretical front, quantum gravity experiments using lab-made analog black holes could simulate horizon physics with sound waves or ultra-cold atoms. While these won't recreate true space-time warps, they might reveal how information escapes evaporating black holes or how Hawking radiation behaves, clues to unifying quantum mechanics and relativity. Meanwhile, AI sifts through mountains of astronomical data, identifying rare black hole flares or subtle lensing events humans might miss. What emerges is a new era where black holes aren't just studied, they're interrogated with every tool humanity can muster. From space-based gravitational wave symphonies to razor-sharp images of spacetime's edge, these missions will transform these cosmic enigmas from mathematical curiosities into understood phenomena. The questions they'll tackle read like a wish list for astrophysics. What happens at the singularity? Do wormholes exist? Is the universe itself holographic? Each answer promises not just knowledge, but a fundamental rethinking of reality's fabric, proof that even the darkest objects can't hide forever from the light of human curiosity. From the monstrous Ton 618, with its 66 billion solar masses stretching space-time like a cosmic funhouse mirror, to the eerie whispers of Hawking radiation proving even black holes aren't eternal, we've journeyed through 30 revelations that shatter our cosmic perspective. These gravitational titans aren't just vacuum cleaners of the universe, they're architects of galaxies, creators of quasars brighter than 1 trillion suns, and even potential portals to other realities. Who could forget Sagittarius, a star's quiet dominance at the Milky Way's heart, or the way photon spheres trap light in infinite loops like cosmic carousels? Or the mind-bending possibility that every black hole might contain an entire universe within its singularity. The sheer scale of these phenomena defies comprehension. Imagine filaments of gas being twisted into relativistic jets at 99% light speed, or mergers so violent they launch black holes across galaxies at 5,000 kilometers per second. Consider how supermassive black holes like J2157 defy physics by devouring a sun's worth of matter daily, or how gravitational lensing turns them into nature's own telescopes, warping starlight into Einstein rings. And let's not forget the haunting sound of two black holes colliding, a chirp in the void that confirms spacetime itself can ripple like a disturbed pond. Yet for all we've uncovered, every answer births new mysteries. Why do some black holes like IC101 grow to 100 billion solar masses while others remain relatively petite? What truly happens beyond the event horizon? Does information vanish forever, or is it holographically preserved? Could primordial black holes from the Big Bang be lurking unseen, composing the universe's dark matter? The more we learn, the clearer it becomes. Black holes aren't anomalies. They're central characters in the universe's story, shaping everything from star formation to the very structure of reality. So here's a question to leave you with. If supermassive black holes anchor galaxies and regulate cosmic evolution, could they be less like accidental monsters and more like cosmic custodians, fine-tuning the universe for complexity, even life? Drop your favorite black hole fact in the comments, and let's keep unraveling these spacetime enigmas together. After all, in a universe where darkness holds so much light, the next revelation might be just one observation away.